Probability lesson. In this lesson, you're going to learn about mutually exclusive events and independent events. Mutually exclusive events, very simply, are two events that can't occur at the same time. Example, tossing a heads and a tails when flipping a coin, rolling a 2 and a 6 on a roll of a die. By the Venn diagram, you can also see that the two events have nothing in common, that is that the circles don't overlap. As you can see too in the orange box, there's a couple of equations that address this. The first is the probability of A and B equals 0. A and B again refers to the overlap, which there is none. And the probability of A union B, which again can be read as A or B or both, is simply the probability of A plus the probability of B. The example says you're given a couple of probabilities, PA and PB, and the PA union B. You're asked to find if they're mutually exclusive. This is simply a test. If they are mutually exclusive, then they must satisfy the equation. Exclusive. So set up the equation. PA union B must equal PA plus PB if they are mutually exclusive. We'll test it. 0.62 then should equal 0.35 plus 0.28, and we can see that 0.62 then obviously does not equal 0.63. So we would conclude then that they are not mutually exclusive. Another example, a student is a marathon athlete. The probability that he comes in first place in the marathon is 0.56. The probability he comes in second place is 0.38. We're asked to calculate the probability if he finishes in first or second place. So again, we can identify the two different probabilities. The probability of finishing first is 0.56. The probability of finishing second is 0.38. And now we can answer the question in A. And the question using the notation is really asking this. What is the probability of him finishing first or second? And again, this is a perfect case of mutually exclusive events, as he can't finish first and second in a race. So the equation will simply be PF plus PS, which is 0.56 plus 0.38, which would equal 0.94. And then in B, the question is asking the probability that he doesn't finish in either first or second place. Really, this is the complement of the answer in A. It's not first or second. All right, so the notation, probability of first or second with the complement is 1 minus the probability of first or second, which would be 1 minus 0.94, which equals 0.06. Another type of problem that we can do are problems that involve sample spaces. And quite often a grid is a suitable representation of a problem. As an example 3, it asks us to use a grid to illustrate the sample space for tossing a coin and rolling a die simultaneously. Obviously you're going to get one set of outcomes from the coin, one set of outcomes from the die. The possible outcomes from the coin are heads and tails. The possible outcomes from the die are rolling any of the numbers from 1 to 6. So this would be a good way to set up a grid diagram. It could also be called a lattice diagram. The first question here is asking for the probability of a heads. To answer that question, we're just going to look at all the intersections that involve heads. And again, you would look along the line that has H. So it would be 1, 2, 3, 4, 5, 6. And the total number of intersections is 12 on this diagram, so the probability is 6 over 12, which can be reduced to 1/2. Second problem, the probability of getting a tail and a 5. So tail and 5. Again, whenever you see the notation intersection, both of those events must happen. So we're looking for the intersection that has tail and 5. there's one of those, and there's, again, 12 possible intersections. So that probability is 1 over 12. And then the last part is the probability of getting a tail or a 5. And in this case, we're going to count up any of the intersections where there's a tail or a 5. Again, there's 6 intersections that have tails, and there's one additional when a head would be tossed and a 5 would be rolled. All right, so if you add up all of those intersections, that should be 7 over 12. Again, we can use a sample space grid for question 4. 2 square spinners, each with the sides 1, 2, 3, and 4 on their edges, are twirled simultaneously. So again, the setup would be something like this. The different outcomes from one spinner, which would be the numbers 1, 2, 3, and 4, and the different outcomes from the second spinner, which would again be the outcomes 1, 2, 3, and 4. Part A asks the probability of 3 on each spinner. It's hard to designate which is which. Sometimes they do it with a color. But in this case, we want a 3 and a 3, and we're looking for that intersection. There's only one intersection that involves a 3 and a 3, so that probability would be 1 out of 16. A 3 and a 1, the probability of getting a 3 and a 1. Again, we're looking for all the intersections that involve 3 and 1, and there's 2 of those. 3 on the top spinner, 1 on the side, or a 1 on the top spinner and 3 on the side. So that corresponds to 2 of the 16 intersections, which can be reduced to 1 over 8. And then lastly, an even result on each spinner. So we want the probability of even and even. Again, probably helpful to identify the intersections that involve even and even. So even and even would be a 2 and a 2, and a 2 and a 4, or the 4 and the 2, and the 4 and the 4 here. And again, simply count the intersections. And you can see that there are 4 intersections, 4 such intersections. So the probability would be 4 out of 16, or 1/4. Next, we'll move on to using the product rule. And we're going to talk about the product rule for independent events specifically. You first need to understand what the definition of independent events are. Independent events simply are where the occurrence of one event has no effect on the occurrence of the other. All right, so the outcome of one event has no influence on the outcome of the second. And the product rule that we use with independence is simply find, again, notice the notation in the second orange box, the probability of A and B, or A intersection B, is equal to the probability of A times the probability of B. Just one thing I'll note here too is that the product rule for independent events can be extended to more than just 2 events. So it could look like this, A and B and C, for example. It can be extended even beyond this. But that probability would be calculated by multiplying the probability of A times the probability of B times the probability of C. And again, like I say, it can be extended even beyond that. In question 5, it talks about an 8-sided dice and a 20-sided dice being tossed together. We're asked to find the probability of getting 2 5s. All right. Another thing you can do is if the event is really long, you can define it. So we can say event A is a 5 on the 8-sided dice, and B will be a 5 on the 20-sided dice. Now in my problem I can refer to A and B instead of writing out the entire event. So now we're asked for, really what we want is we want the probability of A and B, getting in 5 on the 8-sided dice and a 5 on the 20-sided dice. And again, the formula that we'll use is PA times BB. Now it's important to stress here too that we can only use this formula if we know that the 2 events are independent. And again, think about this. Rolling a 5 on the 8-sided dice has no bearing or no influence on whether or not you can roll a 5 on the 20-sided dice. So these two are, it's logical that they are independent, so we can automatically use the independent, or the product rule for independent events. And again, the probability of rolling a 5 on the 8-sided dice is 1 out of 8, and the probability of rolling a 5 on the 20-sided dice is 1 out of 20, for a combined probability of 1 over 160. Again, really important to stress here too is that you can only use this product rule for independent events if you know for sure that the events are independent. Question 6. Again, the information is given to you in the notation form. PA is 0.44, PB 0.25, PA union B is 0.58. Again, we're not told anything about whether the events are independent. So what we first have to do to find PA and B is we have to use the formula for combined events, and that is PA union B is equal to PA plus PB minus PA and B. This is how you have to find PA and B to start. Again, unless you're told that they're independent. A union B, we know the value, 0.58 is equal to 0.44 plus PB, 0.25 minus PA and B. Move the terms as appropriate and add and subtract. You should get a value of 0.11 for the probability of A and B. Now, this is also a typical way that the question will be asked. You can now be asked, are A and B independent? So what you'll do now is you'll use the product rule as your test. So if they are independent, the product rule for independence will be true, and it will give you the same value as you found in part A. So we'll do PA and B then must equal PA times PB, and PA and B is 0.11, the probability of A is 0.44, the probability of B is 0.25, and if those are multiplied, you will find that they are equal. Now, since this equation has given us the same value that we found in A above, we can conclude that A and B are independent now. So therefore, A and B are independent. Okay. In C, now, two events can't be both independent and mutually exclusive, so we already know our answer for C, but we'll do the process anyways if we didn't know. If they were mutually exclusive, they must satisfy the formula for mutually exclusive events, which is PA union B must equal PA plus PB. And again, our value for PA union B is 0.58, PA is 0.44, PB is 0.25. And again, it's obvious that 0.58 does not equal 0.69, which we already knew, but we can say it. Therefore, not mutually exclusive. All right, next question. Question 7. Events in A and B have the following probabilities. Again, we're asked to calculate the probability of A and B. And again, because we don't know whether or not the events are independent, we have to use the combined events formula. So PA union B is equal to PA plus PB minus PA and B. Substitute in the values that we know. 0.85 is equal to 0.4 plus 0.65 minus PA and B. Move the terms around and solve. You should find that PA and B works out to be 0.20. And again, that was part A. And part B, determine whether they're independent. Again, we'll do the test for independence by using the product rule for independence. So again, if they were to be independent, they would satisfy the product rule for independence. We've already found PA and B to be 0.20. PA we know is 0.4, PB is 0.65. Here we find out that 0.20 does not equal the product of those two probabilities. So our conclusion now would be that these events are not independent. In the C part, you can't, now just because two events aren't independent doesn't automatically mean that they're mutually exclusive. It's important to note too that independent events are a specific type of combined event. All right, but we'll test for whether or not they're mutually exclusive anyway. All right, the test for mutually exclusive, they must satisfy the equation PA union B is equal to PA plus PB. Again, PA union B is 0.85 and PA is 0.4, PB is 0.65. Add them up. 0.85 is equal to 1.05, which obviously is not true, and so therefore they're also not mutually exclusive. Since there is an overlap though, there is a value for PA and B. They are some type of combined event. They're just not independent. All right. And then question 8, the classic marbles in a bag question. There's 3 yellow, 4 blue, 2 red. Marbles randomly taken out, looked at, returned to the bag. What's key here too is that it's returned to the bag. We can't do this question in this way if it's not returned. There's another way of doing it. And since there is replacement, now these are from trial to trial, it's independent. All right, because the probabilities stay the same from trial to trial. We'll identify the different probabilities. The probability of getting a yellow is 3 out of 9. The probability of getting a blue is 4 out of 9. And the probability of getting a red is 2 out of 9. And again, it's important to note here too that these are all the possible things that can happen in the question, and all of their probabilities must add up to 1. Within a problem, all the probabilities must add up to 1. So now in part A, it asks, what is the probability of getting 3 blue marbles? So I might use the notation like this. The probability of 3 blue would be, the calculation would be done this way. Probability of blue times probability of blue times probability of blue. Because again, they are independent. And the calculation would be this, 1/3 times 1/3 times 1/3, which would be 127. Part B asks for 1 marble of each color. So again, that would be 1 yellow and 1 blue and 1 red. Again, repeated independent events. Calculation would be the probability of a yellow times the probability of a blue times the probability of a red. And the calculation would look like this. It would be 1/3 times 4/9 times 2/9. It's nice to work with reduced fractions if possible. And this works out to 8 over 243. And part C is the questions asking the probability of getting 2 red and 1 yellow. So the probability of 2 red and 1 yellow. Again, it would be probability of red times the probability of a red times the probability of a yellow. And the calculation would look like this. 2/9 times 2/9 times 1/3. And that probability would be 4 over 243. And that completes this lesson. Go ahead and try some homework questions on your own.